Okay, well, let me welcome everyone to the final session of WOST III. I've been instructed to alert everyone to stay 5 minutes after so that David could give us a little closing summary. But without any ado, I'd like to hand it off to Lorenzo and hear about what he's working on. So thanks very much.
Thanks, Jacqueline. Thanks for having me here, and I will briefly talk in this lightning talk about this work that I did with Michele Campisi on spontaneous fluctuation symmetry breaking and the Landauer principle. Okay, so without further ado, let's just it's based on this work that you find cited down here. Okay, the talk that I will be giving today. So let's jump right into the topic. So first thing we need to look at are fluctuations relations. Okay, I don't believe they do need much introduction for the audience of today, but just to set the notation for everyone, what we will be looking at specifically is the Jarzynski identity. Okay, which for a cyclical process we do know that can be written in this form, where the delta F of the free energy is equal to 0. The Jarzynski identity, the left side, the exponentiated. The mean of the exponentiated work is going to be equal to 1. Okay, and the Jarzynski identity stems from the Tasaki-Crook fluctuation relation, which states that there is a ratio which is dependent on the work of the project of the process for the trajectory of a process and its reverse. Okay, so why are we interested in these quantities regarding a discussion on the Landauer principle? Well, because from the Jarzynski identity, using Jensen's inequality, one can derive the second law of thermodynamics, which is, in this case, the fact that for a cyclical process, the work has to be greater or equal than 0. But Landauer principle also holds for cyclical processes. So in the Landauer principle, one wants to have a reset process, which is a cyclical process, which brings any initial state to a particular reset state. Okay, so being cyclical, everything that I just stated, okay, in general, now should keep working for the Landauer bound, for the Landauer principle as well, and in the special case of reset dynamics. Okay. And so we have the second law of thermodynamics here in the Clausius formulation that holds for any process, okay, and it has a very fundamental nature, at least as far as we know of today. And then we have the Landauer principle that holds only for the reset protocols, okay, so we know that this bound holds only when you are erasing information in a certain sense, okay, and it has an empirical nature, okay, it's not bound from first principles or whatever. Okay, and it states that the average work that you spend to do this erasure protocol is at least kBT log 2. Now, since the reset protocol is cyclical, how can it be that this bound is greater than 0 from what I just stated before? So if we go back to the Jarzynski identity and all these previous slides, I have a cyclical protocol, which is okay. I have a subset of a general protocol, but if everything keeps being valid, the Jarzynski should be equal to 1, and thus the work should be greater or equal than 0, and I would be, in principle, able to observe values below KT log 2. Okay. This is a good moment to point out that this is a consequence of the second law, but they are not the same. Okay, when this delta S is equal to log 2, then the two things they do indeed become indistinguishable. Okay, but this is Landauer principle is not just the second law for the special case of delta S equal equal log 2, just for the reason that I just explained, right? Because when we have a cyclical protocol, we should have the work greater or equal than 0, while in our case we do have not, when the specific protocols that we are doing is the reset protocol. So why is that? In this article that I'm talking about today with Michele, we are putting forward a conjecture, which is that the reason is that along the process of the reset, we have a spontaneous symmetry breaking, okay, of the fluctuation relations. What do I mean by that? So let's consider an Ising model, okay, with n spins and n samples, okay. Weird, and I don't know how to call it, samples. So basically what we know it is that we can repeat our protocol n times and take the Jarzynski, the left side of the Jarzynski by just averaging all the values of the exponentiated work, okay? What we will have is we will observe a probability of obtaining the work which looks something like that. But as we increase the size of the system, since we are working with a 2D Ising model where we have naturally a spontaneous symmetry breaking, okay, that's why we are using the 2D model in this paper, we will have this left peak, which is exponentially suppressed. And when you go and consider the Tazaki-Cruz fluctuation relation, basically you will never observe that reverse trajectories, okay, which give you this left-hand peak in the distribution. And the result of that is that you have two competing limits in this case. So if you first take the limit for the number of samples going to infinity while you keep the size of your 2D Ising model to a finite value, so you do not go to the thermodynamic limit and then you do not break the symmetry, you will correctly have that the Jarzynski identity is equal to 1, as per taking the analytic integral, etc., as everybody knows. But if you do the other way around, so you take the thermodynamic limit of the 2D Ising model, and then you try to repeat your reset protocol a large number of times, this quantity will not be equal to 1, but it will be equal to a certain quantity less than 1, which we, if it's equal to 1/2, will allow us to find the Landauer principle again by using the Jensen's inequality. Okay, so, and this is a conjecture. Okay, this is not a proof. We haven't proved it, but what we could do, and the fact that this is this symmetry breaking in the 2D Ising model means that, and the issue is this two non-commuting limit means that there is a spontaneous symmetry breaking of the fluctuation relation that suppresses the reverse trajectory. So this left peak. So we couldn't prove it analytically yet. Yeah.
2 minutes.
2 minutes, okay. We couldn't prove it analytically yet, but we could do some numerics. So we simulated it using Glauber dynamics, and we simulated for varying number of spins. So this is using a 2x2 lattice, 3x3, 4x4, etc., etc. And you can see that as we increase the size, and we are plotting the probability distribution, as we are increasing the size of the lattice, the peak on the left-hand side of the distribution starts to vanish, okay? Trust me that here is not visible in the reduced figure, but we still have some population on the left of the zero. And what this results when we compute this finite Jarzynski, okay, means that for low value of the size of the 2D Ising model, the Jarzynski averages to 1, okay? Here we took 1,000,000 samples, while as we increase the size of our 2D Ising model, so we break that symmetry that I was talking about, first we keep finding some rare events, which are these kicks in the Jarzynski as we increase the number of samples, and eventually we know that in the limit of n going to really infinity, this will kick by kick will come up to 1, okay, as it should be. But we see that quickly as we increase the number of spins, the Jarzynski actually becomes equal to 1/2, and it's really rare to pick up the rare trajectory that allows you to resum back to 1. How rare are these fluctuations? Well, we know that from the work of Jarzynski himself, that the probability of observing a rare trajectory scales as the exponential of the average work. And so we can see that as we increase again the size of our lattice, if we are above the critical point, which is around 2.6, 2.7 for the 2D easing model, we do have a high probability of observing the rare events, and the Jarzynski will resum to 1 correctly. But if we go in the regime where the symmetry is broken, and we go in the thermodynamic limit, so we make that non-commuting limit as we were discussing before, we observe probability of observing rare event, which decay really, really quickly to values, which means that that are so small, that means that you can do the erasure for the, I don't know, forever, basically, and never observe a reverse trajectory. Okay, so even if analytically you should, so by taking the integral of that average in the Jarzynski, you will eventually observe. So if you go really to infinity with your number of repetition, observe a rare event, which will make your summation of the Jarzynski sum back to 1. In practice, you will never observe that. And so these events are practically impossible to observe in the spontaneous symmetry breaking regime. And what we conclude is that while the second law is the direct consequence of the fluctuation relation, the Landauer principle is a direct consequence of the breakdown of the fluctuation relation, in the sense that I just explained, that we do no longer resum back to 1, but phenomenologically, we have a limit that prevents us, a symmetry breaking that prevents us to actually observe the reverse trajectories. So thank you, and I'm open for questions.